Thanks again, everyone, for coming for another space science seminar series. My name is Jason Schuster, and I'm happy to introduce our speaker today, our very own Matthew Argall, new research associate professor in our department as well. So congratulations to Matt for that. Matt's background, of course, he hails from Augsburg in Minnesota, where he did his undergrad in physics and mathematics, and then graduate work here at UNH, actually, for his master's and doctoral work. And some fun facts about Matt you might not know. He is the proud parent of two little ones. Alice, 1.5 years old, and Maxwell, 7 years old, I believe. Matt's the soccer coach for Max's soccer games, so which a couple more left in the season, I think. And I'm curious if Matt named Maxwell in part after maybe Maxwell's equations, which are very, look forward to the work we do here potentially. So, but in any case, we're very excited to have Matt here. And if you stick around after, you can see me getting lost in virtual reality and the headset that Matt has brought as well. So with that, take it away, Matt.
Thank you. So I'm here to talk about my research, some related to space weather, with the space weather follow-on mission, and also doing some outreach stuff. So space weather is a big topic nowadays, now that we're going into solar maximum and apparently now reached solar maximum. Lots of things happen as a result of space weather. One is the nice auroral displays that we've seen the last once in a while, the last couple months. We also have to protect our astronauts from energetic particles, from radiation. Our satellites can be damaged. They can cause radio blackouts and power outages in our electrical grid. And so there's a lot of industry interest in predicting space weather and studying space weather to protect our human, biological, and ground assets. And so, as I said, space weather's been in the news a lot lately. Back in 2022, SpaceX lost 40 satellites because they launched them too low, and the increased drag caused them to deorbit. And lately we've had a couple of nice auroral displays that we could see from New Hampshire. This one here is seen from my backyard. And that's a picture my wife took, so it's pretty nice. It doesn't look so good with your own eyes, but the camera brings it out pretty nicely. And so as I mentioned, it's important for us to try and predict space weather. Currently, NOAA has a real-time space weather asset at one point between the sun and the earth in Discover, and ACE also provides real-time data. The next generation of space weather information is going to come from the space weather follow-on, the Range 1 mission, which we're providing the magnetometer. So you can see the Swiffle L1 satellite here. The magnetometer is at the end of this long boom, and here's a picture of the magnetometer that we are creating. This is the engineering unit. The flight unit is currently installed. There's actually two of them, an outboard sensor here and an inboard sensor here. And it'll be launched sometime next year. And with this data, they're able to provide real-time data products to the community and to industry, as well as predictions of different quantities of interest. And so with real-time data from L1, I'm in charge of processing the data, and so we need to be able to process that data in real time. So I'm setting up our own real-time space weather center at UNH, and in addition to the Swiffle L1 magnetometer data that will be shown there, we're also developing real-time machine learning models. This one predicts the global intermagnetospheric electric field, and so we'll have real-time predictions of the state of the intermagnetosphere as well. So space weather is often a result of something called a coronal mass ejection, which is essentially a giant flux rope that gets pushed out towards the Earth. It's moving supersonic, faster than the solar wind in front of it. And it often causes a shock with a shocked turbulent plasma, but ahead of the CME. And those are they're very geoaffective, so they cause all of the space weather effects that I showed in the previous slide. And so in addition to trying to predict space weather using the space weather follow-on mission, there's also this helioswarm mission that UNH is a part of. And it's a swarm of 9 satellites with the goal of studying the evolution of turbulence in the solar wind. And it can do so from ion kinetic scales up to MHD scales. And so you can see different spacecraft separations here around ranging from MHD to kinetic scales. And so in looking ahead to these missions, I will show some data from the Sheath region of the CME and see how it evolves from L1 to Earth. So well-studied CME occurred on the 23rd of April in 2023. And here's some data for that. The magnetic field from wind and MMS are shown here. So wind is at L1, MMS is near Earth, just upstream of the bow shock. You can see here the model magnetopause and model bow shock for this event, along with the MMS orbit and the location of MMS. And then the energetic particles here clearly showing very energized plasma. So the shock arrives at this blue marker here, and you can see the solar wind transitions from a weak, steady solar wind magnetic field to a very turbulent region within the sheath of the CME. And then behind the sheath is the magnetic cloud, or the flux rope and magnetic ejecta. And that's also very more quiet and not as many energetic electrons. There's this interesting region over here where the density is very low and the plasma is subalfanic. And when that happens, when the subalfanic region passes by, what we see is that the magnetotail, which is normally in this stretched configuration extending out very far behind the Earth, transitions to alphane wings. So it actually closes up on itself and doesn't extend very far back into the solar wind. So these are an overview study and a modeling study of this event, of the entire event. What I'm looking at in particular is this sheath region where we see lots of turbulent magnetic field and energetic plasma. So again, I show the sheath interval here with wind and MMS on the bottom. And so if we look at the power spectral density of the magnetic field at wind, we can see in the inertial range, the MHD scales, Kolmogorov-like turbulence spectra. So very typical of the solar wind, even though we're in the CME sheath. And then when there's a spectral break between the ion inertial length and ion Larmor radius, and the slope increases to minus 2.8, which happens to be considered a universal dissipation rate in the solar wind. So at wind, we see in the CME sheath, we see properties of magnetic turbulence that is very, very typical of the solar wind itself. As we move towards Earth and see the same interval with MMS.
Excuse me, Matt, can you explain to us what the difference is between the top and the bottom?
Oh,
panel?
yes,
I mean,
yes.
Also, the slope doesn't seem to be what you're indicating there, right? I mean, if it's k to the minus 1.7, I mean, it shouldn't be a flat line. I mean, it shouldn't be a horizontal line. It should be something else, shouldn't it?
So right, okay. So the top panel is a typical power spectral density. The bottom panel I've normalized the spot power spectral density by the spectral index in the inertial range. And
Okay, so you multiply the whole thing by k to the minus
Right,
1.7.
right, and this way I can see that my slopes,
Okay,
the
so you see
slopes
the
that I
deviations.
determined are
Correct,
correct,
yeah.
yeah. And then this gold line is a sliding 1 decade median average. Alright, so this is the same type of plot at MMS. So if you notice that wind, I guess it doesn't extend fully past the ion kinetic range. But MMS has a search coil, so a flux gate measures the DC component, a search coil measures the AC component of the magnetic field. And we can see just beyond the lower limit of the ion scales, sort of crossing near closer to the electron scales here. And we see a similar Kolmogorov type scaling in the inertial range, so not much is happening at large scales, but at ion kinetic scales, the slope increases. And so between L1 and Earth, which are often in interplanetary scales considered to be the same spot, yet we still see this change in dissipation rates at ion scales. And so we can look a little bit further into the sub-ion scale range by noting that the spacecraft separation of MMS is small at smaller scales than what we can achieve just through single point analysis. And so we can look at the equivalent spectrum, which is based on the single point and multi-point structure functions, which is basically the length difference for single point measurements or the interspacecraft difference of the magnetic field for multi-point measurements. And so the power spectral density on the right is shown in sort of transparent gray and blue. And then the equivalent spectra is this black solid line for FGM and the blue solid line for SCM. And one thing to note is that the equivalent spectrum doesn't have the spectral break that we saw in the PSD. And that's usually because the interspacecraft separation is often not along the flow direction. So for single spacecraft measurements, we assume that everything is frozen in and propagating with the solar wind. And so we can convert spatial time scales to spatial scales. But if you have something like anisotropy in the turbulence, you can't necessarily do that. But if we look at the multi-spacecraft estimates of the equivalent spectrum, they follow this steepened spectrum at k to the minus 3.6. And so I take this as the slope continues at minus 3.6 down through the sub-ion scale.
And Matt, is the other blue curve there, the blue spectral plot, like it goes to very low values on the left, is that part of SCM?
Yeah, so this is SCM, which only measures the AC field, so below 0.3 hertz. It's high pass filtered, so in the other plot I cut it off, so you can see it dip down here, but I cut it off. All right, and then another difference between MMS and wind is that this purple line is the breakpoint at wind, and the red line is the breakpoint at MMS. And at wind, between those regions, the spectral index is minus 2.8, but at MMS it becomes shallower at minus 1.6 again. So there's some amount of propagation of energy from small scales to large scales, at least within this region, which I find is interesting.
I mean, is that strong argument that you can make, or could it be just somewhat with the data? I mean, it's hard to believe that on the scale from, what is it, 200 RE or so, you know, which is just 30 minutes or so, I mean, propagation time, I mean, the spectra really change that much, because, I mean, if you assume that, you know, I mean, the spectrum should change dramatically, you know, let's say from 0.5 AU up to the Earth, you know?
Yeah.
I mean, this is so, it's
So-
a little hard to believe. I mean, I would rather look into whether there are instrumental effects, you know, or maybe the presence of the foreshock or something like that.
Yeah, I've looked for foreshock and I haven't seen it. Although later the bow shock does move outward, I don't see presence of the foreshock and during, like, just before this time interval at least. But again, like the evolution of turbulence between L1 and Earth is often overlooked because on interplanetary scales, when you're looking at CME propagation, usually they're considered coincident. And so I found maybe one article that studies CME turbulence or CME evolution between L1 and Earth. And so this is somewhat new, and I haven't found anything yet in the data that would make it seem like it's a data issue, but I mean, so I'm fairly confident that it's real.
I mean, that's basically my question, you know, I mean, can you really confidently say that, you know? I mean, yeah, if you can, that's,
especially,
it's certainly a result, you know, and
Yeah.
the fact that nobody published it, you know, may be due to the fact that nobody could confidently say that, you know?
Yeah. and
I
so,
mean, if you write a paper there, you know, and, I mean, you might just get shot down by the referees, you know, I mean,
and so one reason for showing these multi-spacecraft results is to confirm that the spectra break and the slope really does increase. It's not just single instrument, it's consistent across multiple.
Okay, another stupid question, I mean, there's a possibility that you have a third spacecraft out there, you know, like Themis maybe, or.
Themis is out there, but more on the dusk side. I haven't looked at Themis data, but I can.
Yeah, because.
Have you looked at all, like, so which MMS spacecraft is coming from, MMS-1, 2?
I'm focusing on MMS-1 for the single spacecraft measurements, but these points here are from a combination of all four.
So just the average of the tetrahedron then? Or-
They're increments across spacecraft, so between 1 and 2, 3 and 1, 3 and 1, 4 and 1, 3 and 2, 4 and 2, 4 and 3.
Okay.
So it's
Okay, now I understand the figure, so that's really those points down there.
Yeah.
I mean, okay,
yeah, so the spatial scale here in kilometers is just 1 over the spacecraft separation here. And
Okay.
then the increments to get equivalent of PSD units, it's the change in magnetic field squared over the time period.
now that would be really significant, because now you, that's an order of magnitude, right?
Yeah. Yeah. All right, so then just quickly, looking at all three components, the X and Z components are very similar, but the Y component doesn't show the same shift in spectral breakpoint between wind and MMS. And so whatever this change in dissipation mechanism that occurs on the way to MMS isn't present along the Y component, indicating some sort of anisotropy in the turbulence. I haven't looked at the source of the turbulence or anything. I haven't done a wave analysis or anything to know that, like, a dispersion relation to know what the source is, but it seems to be anisotropic.
Which way is the local DC magnetic field pointing here?
Mostly along Z, I think. That's a good point. So,
Is the obvious source of anisotropy would be that you've got one value along the field and a different value across the field.
yeah, so Y does appear to be the smallest component over the entire interval. So it could be that, in a field aligned coordinate system, Y might be like the minimum variance here.
So you might wanna do the analysis in
Yeah,
field aligned and perpendicular, you
Yeah.
know, I mean, that's. And if I remember correctly, I mean, all the theoretical and simulation work by, what was it? What the names, I mean, that they talked about this, what they call the Maltese cross, you know, so if you actually plot that in a parallel versus perpendicular plane, you know, the K vectors, you know, I mean, they
Yeah, yeah.
align with the two
Was Bill
axes.
Matthews doing some?
Bill
of that?
Matthews, yes.
He's a Delaware.
No, but there was also Goldstein, right? I mean, there was
Okay,
Goldstein,
yeah.
Goddard, you know. And they did things like that, you know. I don't know whether that, I mean, this is old, you know, it's like 20 years, 30 years old, you know, so I don't know whether that still holds today, but I mean. I'm just wondering, I mean, because the other thing that I remember from all these studies is that it is actually what's observed is usually much more isotropic than it should be. And people scratching their head because the -5/3, I mean, it's for fluid theory, you know, it's for fluid theory. And
right.
it should not really hold for MHD, and, but often it apparently does, so, and I thought that was a conundrum that hasn't been solved, so. But I don't, again, old stuff, you know, I mean, I don't know whether it's anything new.
Yeah, definitely, future step would be to look at subintervals within the sheath and also, look at perpendicular versus parallel, dissipation. And so, then knowing sort of the general properties of turbulence as it relates to the power spectrum, we can look at intermittency, which can tell us, the distribution of the fluctuations as a function of scale by taking sort of the difference between adjacent points at different lags and histogramming them. And then if you calculate the kurtosis of the distribution function, which is the third moment, it can tell you fourth moment.
This is for it,
Yeah, it can tell you how non-Gaussian these tails are. So if you have non-Gaussian tails, it means you have an abundance of large amplitude, small scale fluctuations. So a Gaussian normal distribution is shown as this magenta curve. And then as a function of scale, so these colors here correspond to these colors here. So I'm taking at MHD scales, ion inertial length, ion Larmor radius, the spectral break, and ion inertial length. And you can see from the value of the kurtosis that it becomes more intermittent as you go towards ion scales, but around ion scales it's somewhat constant. And if you look at MMS, MMS has a point beyond at scales smaller than the ion inertial length, and there the kurtosis increases significantly. So below ion scales, you're starting to generate more and more larger fluctuations. But interestingly, the increase in intermittency is not due to an increase in the largest amplitude fluctuations, but instead a decrease in the intermediate amplitude fluctuations. And so it seems like the large amplitude fluctuations are being left alone, more or less, and that the energy being dissipated in ion scales is coming from these intermediate fluctuations. And so far in the literature, when I hear about intermittency, it's always talking about the ends of these tail regions. And then some large scale structures that are persistent from wind to MMS. So you can see these sort of linear ramps in the magnetic field that shows up in as a high probability of finding slopes that match this fluctuations that match this slope.
Which begs another question. The wind satellite is not exactly on the sun earth line. I mean, they're about what, 50
Right.
area off, 80 area off, you know. And MMS wasn't exactly there either, you know, so
Right.
how are they actually aligned? I mean, it's
Yeah, I haven't plotted the exact position of wind yet, but that's something I need to do. I mean, with respect to MMS. But yes, there's a lot of debate right now. How well does the upstream solar wind allow you to predict the conditions at Earth? And
well, I mean, that's been around for
Yeah.
50 years.
yeah,
And it depends on the scale, you know,
Yeah.
I mean, the large scale, if you have a CME, you know, a nicely formed CME, yeah, it's
Mhm.
perfectly correlated, you know, but on a minute time scale or 5 minute time scale, you know, maybe not, you know,
Mhm.
so.
Right.
Easy to do, I mean, the
Mhm.
correlation, I mean, just do the
Yeah.
shift and see, I mean, how well they match.
Yeah. I'll talk about that in a couple of
All right,
slides.
sure,
Mhm.
sorry.
Sorry. So again, looking at all the three components, X and Y, or X and Z are roughly the same. In MMS, you can see the increase in kurtosis at subion scales. But the Y component again is different with no significant increase in kurtosis at subion scales. Which is again consistent with the fact that it didn't show change in spectral breakpoint or slope in the power spectral density. So if we ask what type of fluctuations are occurring, we can take the increments and normalize them. And so the normalized increments of the magnitude of the magnetic field is called the compressibility. And so alphanic fluctuations are incompressible and they have compressibility values of 2 or less, whereas current sheets are very compressible and would give you values of compressibility beyond 2. And we see that all the fluctuations have a nice cutoff both at wind and MMS at 2, indicating that they're alphanic in nature. So this is some sort of alphanic turbulence that's happening. So the last thing to check is the correlation length between L1 and Earth. And so we just take the correlation, the autocorrelation at wind and MMS, and just and then fit this to an exponential to get the correlation length to see beyond what scale does one parcel of solar wind no longer look like the next parcel of solar wind. And so at MMS and Earth, it's on the order of 10 to the 4 kilometers. And again, all three components, X and Z, look the same. The Y component very nicely fits the frozen in condition. Whereas the others deviate, the data deviate from these fits, indicating that they're not so well frozen in. And also the correlation length along the Y direction is an order of magnitude smaller. So again, indicating something is different about the Y component. And if I do a correlation just between MMS and wind, I don't show it here, but the correlation, the two spacecraft correlation between wind and MMS matches nicely these curves here. All right, so I guess that's all I had to show for the turbulence for this event here. Or I move on, any questions from this? Yeah,
Where's this spectral break with respect to the physical plasma scales as opposed to kilometers?
yeah,
Does that change from L1 to Earth?
it does. The ion Larmor radius is this first blue line, the ion inertial length is the second blue line. And you can see that again, here here on the MMS side, it's these two blue lines, and you can see that the shift from the purple to the red is getting closer to the ion inertial length.
So even though they may be different in kilometers, they may be closer in terms of the plasma scales, if you normalize to that, or is it the other way around?
So I've used the average plasma parameters at wind to calculate the inertial and length and the armor radius, and the average plasma parameters at MMS to get them here. Does that answer your question?
I mean, so it's for the whole ensemble of spectra that you calculate the plasma scale, not for the specific
I do it for,
specific interval where the spectrum was calculated.
yeah, so the spectrum is calculated over this entire interval here, and the average plasma parameters are also calculated over that mark. Yeah.
Yeah, but if I look at that, I mean, I can see some intervals that are very distinctly different.
Yeah.
You see some intervals where you only have small fluctuations, where another you have the other,
Yeah.
one, so
So there
so
are,
you're mixing that all up, maybe
Yeah.
that's not such a good thing to do.
yeah, there are
Right,
some, there are
Yeah.
some,
Yeah, if you're using Fourier methods, then you implicitly assume stationarity over the
Yeah.
interval, and that looks like it's problematic.
yeah, there are some, usually studies that look at propagation from, say, Mercury to Earth or beyond. Analyze the entire sheath interval as one interval. But there are other studies that analyze just the sheath region, and they look at the region immediately following the shock as one region, and then the region immediately upstream from the magnetic cloud as a separate region. And as you can see, they clearly, so the region upstream from the magnetic cloud is thought to be solar wind plasma that was there before the CME was created, and it's just propagating along with the CME. Whereas the plasma just behind the shock has been affected by the shock. And
Yeah, well, in your case, I mean, it all has been affected by the shock, I mean, both the intervals are looking at, so there's no difference. But I think it might be interesting to look at, I mean, there's a relatively quiet period there in the middle.
Yeah.
So if at all that develops between, or changes between wind and MMS, if there is actually changes there, so
yeah, there
it might be.
are discussions of planar structures in the solar wind, and I'm not familiar with the significance of the planar structures, but this appears to be one. So I need to look into what a planar structure would imply.
And actually here in your plots map, this is showing B from wind and also from the mess just below it.
Right.
So you kind of see there is that sort of quieter chunk on both spaces.
Yeah, no, the quieter part is in both of them.
Yeah.
You know, so, but the question would be, I mean, that I would ask, does it actually develop between wind and MMS, just that quieter part? Is there some development, I mean, you certainly see development in the other components, I mean, that's another exercise I would do, I mean, just off the bat, do the time shift. And plot the individual components over each other.
Yeah.
Between MMS and wind, and you immediately see, I mean, that there are certain features that line up and other features don't line up,
Yeah.
I mean, and it's a typical thing, I mean. Yeah, what does it tell us? I don't know, I mean, there are discontinuities within the solar wind there, which are, well, if they're TDs, they would just passively convect along, but if there are these, they would actually propagate between wind and that, so, yeah.
Could you also possibly get ACE data during this time?
ACE is probably available.
It might be interesting to compare wind and ACE, because just to see if there's any.
Oh, yeah, well, if you have
I'll talk to Chuck.
anything you can get your hand on. I don't know whether Geotel still produces data, I think that.
ACE is available. And
I mean, but,
Are you looking at ACE?
yeah, ACE is available, share the similar distance as wind. So you can also have therms B and C, which is around 50 Earth radii upstream of the Earth. So you can also see how the structure evolved from wind to thermals and then to MS.
Okay.
The other thing I think you need to do, and you have to be very careful there, these data are dirty. I think I can even see that on this plot, again, if I had a laser pointer, it would be great. But I can show, wind often has spikes, in the magnetic field data. And if you look at the end of the quiet interval in wind, okay, in the red curve, exactly there, there's a, and it's only one component, that already is fishy, And if you plot it, on a different scale, you might actually find out it's just bad data, And especially once you start averaging, things get worse, you don't see it anymore, There may be 100 nanotesla spike, in the 16 hertz data, Now it's averaged down, you still have a spike, but it almost looks real, So you gotta be really, really careful with this thing, So,
Okay.
and especially, well, it's bad for us when we do simulation with bad input, but it's also bad for you if you do a spectral analysis with that,
Right.
Because such a spike, gives you a extra modes, which are not there.
Garbage in, garbage out.
Yeah,
Yeah, sure, garbage in, garbage out, but there as well, so yeah, this is, MMS, I don't know, I wouldn't say anything bad about MMS, and you don't see those spikes in MMS, right, in MMS data, but again, I would make 1 hour plots, and at the highest resolution wind, I think comes at 3 seconds.
Okay.
So, which is not how they measure it, I think they still measure at 16 hertz, but I'm not sure whether they actually transmit that.
Robin, you have a question?
Yes. Yeah, I have a question about your first slide on intermittency. So you said, that some of the kurtost tails were, some of the majority of the energy dissipation was going on at the intermediate scales, right? Because how did you determine that was where they mismatched the most? Because also isn't the mass under the PDF conserved? So if you remove it from one place, it's gotta go to some other place anyway. So like if the tails, mass is removed from those intermediate regions, it's gotta go to the tails or somewhere else.
not if the energy in the magnetic field is going into the plasma.
Okay, so
So so the scale length, is taken, so intermittency, you calculate the increment of the magnetic field, which is the difference between one point and another point.
Yeah.
And each of these curves has a different time separation between the increments.
yes,
So,
I would also think that there's no guarantee that the amplitude is the same. The PDF, as you say, is normalized, but
yeah,
so did that discrimination about the dissipation come from comparing these PDFs? Or
yeah.
are you just
so-
showing where those occur on the PDF? Like when you made the conclusion?
So,
was it-
my conclusion comes from comparing, for example, take this blue curve.
Yeah,
So, so my question is why do I go from a kurtosis of 5.8 to 29?
yes,
And that means we're becoming more non-Gaussian.
Yep.
So something is happening to make it deviate from this magenta curve. And if I look at the largest scale fluctuations, they're all pretty much the same. The
Yes.
probability of occurrence is the same. But if I look at here, for example, the blue curve is more probable, like a value of 3 is more probable than at the purple curve.
okay,
So the intermediate amplitude fluctuations are becoming less probable with scale size.
I see. So you're kind of just comparing the difference in the two curves by eye here.
Mhm.
All right. It would be cool to see a plot of like the actual difference between each pair of curves or the pairs of relevant curves.
Okay.
I understand.
So you're saying like take the blue curve minus the.
Yeah, we're divided by,
Okay.
and what's appropriate.
I guess, that would quantify the differences between the curves potentially.
right, and, For that comparison, you really want to do it with the unnormalized curves.
Mhm.
Is that tells you whether you're just, whether, if you have a difference, is it because you're subtracting the energy in that particular energy range, or is it due to energy being added everywhere but that range?
Okay.
Yeah, thanks for your answer.
Yeah. All right, so, I showed one way that we can use, so this is MMS up here with its 4 spacecraft. With the equivalent spectrum, I showed how we can take the difference in magnetic field values between the 4 spacecraft to calculate the equivalent power in the magnetic field at the scale size of the separation of the spacecraft. Lots of other multi-spacecraft methods that you can implement. And Helioswarm has 9 spacecraft, and we'll have several tetrahedra at the same time at different scales. And one thing that we can do with the MMS data currently and Helioswarm data in the future is to perform reconstructions. So Helmholtz theorem says that if you know the value of a field, its curl and its divergence everywhere on the surface, you can reconstruct that field everywhere within the volume. And so we can apply that idea to the data from MMS with the magnetic field. We know the current density, and it's measured at each of the 4 points. We know the divergence of the magnetic field is 0, and we measure the magnetic field. And so with that, we can reconstruct the magnetic field in and around the tetrahedron, the volume of the tetrahedron. And so,
Under certain assumptions.
yeah. So we can apply that technique under those assumptions to the data, and it's been done several times, and you can see nicely it results in 3D magnetic field reconstructions. I thought that this would be a very great tool for outreach to get kids and even scientists to start playing with the data and interact with data. And so I built a space station around this data cube that has reconstructions from MMS in it. So there's a media and learning room where you can go to learn about different missions, different instruments. There's a model of the MMS spacecraft here, a laboratory over here for playing with instruments and other things. An observation deck for looking outside, and it also has a nice hologram of Earth, Moon, Sun, and the Swivel mission, and then some controls here for interacting and playing with the data. So here's just a movie with an overview of what the environment looks like. So this is so here's the laboratory. You can see some instrumentation on the left that I'll show later. Different instruments, and there's a miniature MMS spacecraft with its booms deployed over there.
What does that binder do at the
You can grab it and throw it or slap it around and it floats around.
So it's a zero gravity room, so.
Some things are 0 gravity, other things are not.
You don't want to have that strobe fly.
Yeah, so this stuff you can pick up and inspect it. This is the MMS EDI instrument, the electron drift instrument. These are the Swivel L1 magnetometers. And then these are the adiabatic invariants in a bottle. So they have they show the gyro motion and then the magnetic mirror, things like that. You can pick it up and look at it. Whiteboard you can write on.
You don't run out of ink with the markers either.
Here's the media room. You'll see it in a bit, but there are models around the outside. Here's MMS. There's EDI and things there. And if you press a button, they show up in the hologram, so you can look at it in more detail. There are the video games here on the right that are like old school 80s arcade games, but they have a two-dimensional cut of the magnetic field as the background, and so when you're playing Pong, the Pong ball will follow the magnetic curvatures, and so it's neat to see how the particle interacts with the magnetic field while playing the video game at the same time. Here's the viewing room and the data space. So here's our data cube. It has the 3D reconstructions in it that is bounded by the white box. Then there's a 2D cut on this gold plane that shows up here. You can see the magnetic field contours and the current density. And you can, with the controls here, you can move this plane forward and backward through the data space. You can change its orientation from XY to YZ to ZY. And you can look at both the magnetic field and the electric field. You can create particles and throw them into the data space, and they trace the magnetic field lines through the data space. It has a fully implemented Spark particle tracing pusher in there. And these little wispy things there are sort of streamers along the magnetic field lines. So and there's Earth back there, MMS satellite, the moon. More laboratory equipment. Okay, so that's an MMS magnet, Swiffle 1 magnetometer.
Okay, so someone with the virtual headset on, I mean, would have the controller and could fly and go anywhere.
Yeah, so it's all. These are teleportation pads. If you point to them, you teleport to them. So if someone gets motion sick in VR, you don't have to move around, you just teleport nicely.
Somebody give them a bucket.
You can also, if you look at your hand, a little, like a virtual joystick pops up, so you can grab it, move it forward, backward, and you can strafe around. So this is an overview of the laboratory, the media room, some different assets that we have in there. I showed you the MMS. There's a Earth with a dipole magnetic field. Want to get a IGRF magnetic field and a Zinyanko magnetic field in there would be nice. The MMS EDI instruments with OL1 magnetometer and some lab equipment with an adiabatic invariance in a bottle. There's a spacewalk and data platform and different visualizations we can have with the data space. If you point, so for example, if you point at somewhere on this 2D cut in the bottom panel, it creates it traces out flux tube at that point in 3 dimensions. And so this is that 2D plane here with all of the flux tubes that intersect with that 2D plane drawn out. And then here's a bunch of test particles that are being traced through the data space, and then again the 2D plane.
Are you showing a reconstruction of like any of the particular event?
Yeah, this is the Torbert magnetotail EDR event. And yeah. And so we've taken this to the New England Fall Astronomy Festival. Jason was there, and so Jason was there. Is it Jason? Chris Pritchard was there. I was there with my son Maxwell. And we were showing it to whoever wanted to put it on. All the kids there were super excited to play with it. It's really fun. Looking to do more outreach activities at local schools, museums, and planetariums in New Hampshire, Maine, and Massachusetts. Anywhere within a day trip of UNH. And then also try and do two high profile events, maybe at the AAPT meeting or Kennedy Space Center would be cool. I'm gonna show it at the AGU meeting. I have a poster, session ED21E. It's a session geared towards using virtual and mixed reality in the classroom. So if you're interested, I'll have my headset there and you can come look at my poster, try it out. And I also want to get more models into VR. So not just from the MMS community, from the UNH community, we're big in
Real models. Real models.
real. Yes, real models. So if you have a CAD drawing of any one of your instruments or anything, I don't see any experimentals in here, but. What happens is you take your CAD drawing and you can export it as a STL file, so that takes it from like a 3D drawing just to a surface of the surface mesh of the polygons, or polygon mesh of the surfaces. And this is generally many more polygons that can be efficiently rendered in virtual reality. So we take it and we sort of smooth it out, so there are fewer polygons to play with while still maintaining the overall structure. And then we apply textures to it, so it looks like the real thing. And so from the CAD model to the reduced polygon mesh to the final animation, looks like this. And so here's the before and after. So it still doesn't look exactly like it, but all the key features are there. So I've received a couple of comments about intellectual property rights and stuff of these models. I'm hoping that with the reduced model, if you export the model with a reduced resolution, there won't be any concerns about intellectual property. And the final product is just a very textured polygon mesh. So, yeah, I'm hoping not too many, to get more models in here and we go through this process. So again, we have the EDI and magnetometer in here. That's a picture of a picture up here, but that's a picture of the real EDI through the plastic clean room wall. And then this is the picture of the EDI magnetometer with its model. And then making use of it, I showed examples, but we have things in the laboratory that you can interact with. We have showcases in the media room and things like that. So I don't have a final slide, but that concludes my presentation, and I have the VR headset here that you could try out if you wanted to after everything is done.
Cool. Well, let's thank our speaker.
So who did this whole thing? I mean, is it you or?
No, I won a grant for this, but I don't do any of the work for it.
So
Southern New
yes,
Hampshire University, they have an inkwell studio.
Who?
Southern New Hampshire University,
Southern New Hampshire, yeah.
they have
No, we did some, okay, sorry.
they have a inkwell studio, which is their game development and design
Yeah.
major, and they have a lot of virtual reality.
Because there are people here at your age, I mean, and what, I mean, just before COVID, I mean, we did something with our simulations and with headsets and I mean, creating GLFT files and all that. And then COVID came, so these
Yeah.
people were actually reassigned to do the COVID whatever
Yeah,
software. And so this fizzled out, you know, so we have done this with simulations already, you know, you can
Okay.
do, I know you can do pretty incredible things,
Yeah.
you know. And so the file format that you use is GLFT or what in the end? What
In
the
the
headset
end,
means. I mean, that's one of the formats they
I will
can.
have to get back to you.
Yeah.
Oh, yeah, so this is just one of the format, it's a animation GLFT, yeah,
Yeah, so because we actually created GLFT files of the magnetosphere, you know,
okay.
if you have I mean, I'd have to look at it, I mean, see what they are. And so, yeah, so, Juan Carlos, I mean, he did that with Blender, I mean, so.
Okay.
Blender data, and so there's some software around, I mean, we can do something with simulations. you know,
Yeah,
so-
I'd like to get some simulations.
So, I mean, we were just in the stage of iterating to make that nicer, you know, and all that,
Mhm.
but that's when COVID came, but now we have
Okay,
5 more years of development, you know.
yeah,
Because size was an issue, that was an issue, I mean, when the files are too big, you know, things don't really work that well,
Mm.
you know, so but these days, the
Yeah,
much
so
better.
if you give me a file, I can give it to my design team.
Yeah, I have to look that up, I have to see what you have.
You could in theory go off the spacewalk toward Earth and like jump around in the magnetosphere or something.
No, you can walk through the magnetosphere, you know, so this was static, so it was not time dependent, it would be nice to have something that is even time
Yeah,
dependent.
I'm working on that for the
the
reconstruction data too.
The other thing that excited me about that was that there is, if you don't have a VR, you don't need the VR set, you can actually, there's a GLFT viewer, I mean, on the web or multiple actually.
Mhm.
And so that means it is a format that can be used in publications. You see, I mean, we have done,
Okay,
people have, not just we, other people too, have done nifty stuff, you know, over the last 30 years or so in 3D.
yeah,
But it's not publishable, you know, you
Yeah.
could never publish that, you know, so, but nowadays you basically can, you know, you can put it in GLFT file, I mean, in the appendix or the supplemental material
Yeah.
for a paper, you know, and people can go through that.
yeah, that's another thing that I would like to do with this is like use the data, explore it and make it useful for someone to include in their publication.
Yeah,